Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing with our investigation into reactions of aldehydes and ketones. We've been looking at reduction reactions. Last scribblecast lecture, we looked at reduction to form alcohols. In this scribblecast lecture, we're going to take a look at reduction to form hydrocarbons. We're going to begin with a look at the Clemmensen reduction. Now, the Clemmensen reduction is a reaction that we were actually exposed to last semester when we examined the reactivity of aromatic rings. Specifically, we examined Friedel-Crafts acylation. If you recall, Friedel-Crafts acylation involved the reaction of a benzene molecule with an acid chloride and AlCl3. The AlCl3 reacted with the acid chloride to produce a psyllium ion, which was a reasonably powerful electrophile. And a psyllium ion would look like this. The AlCl3 abstracted the chlorine, and you got the positive charge here. Now, if you recall, this carbocation would not shift because it was resonance stabilized. The lone pair could dump in, and the resonance stabilized the psyllium ion was sufficiently stable so as to prevent shifting. Of course, it's not this shape, but I'm leaving it like this. Because it was unshifted, this electrophile would go for the aromatic ring, form the benzenonium ion, and you would produce an aromatic ketone. Now, Friedel-Crafts acylation, what happened next was the Clemmensen reduction. We never called it that, but we pointed out that you could make the unshifted alkylbenzene by reducing the carbonyl to a hydrocarbon. This was done using the reagent zinc mercury in HCl. The reagent zinc mercury in HCl is the Clemmensen reduction, right? This part of the equation. That's the Clemmensen reduction. Reaction of a carbonyl with zinc mercury HCl, reducing it to a hydrocarbon. And in the aromatic section, this was nice because it gave you an unshifted product. Whereas Friedel-Crafts alkylation, when you formed carbocation, you had to watch for 1,2 shifting. Now, the Clemmensen reduction is very nice. Zinc is a fairly powerful reducing agent. Zinc mercury is referred to as zinc amalgam. And the mercury essentially acts as a solvent for the zinc. Mercury, remember, is a liquid metal, and the zinc dissolves in the liquid metal. Now, depending on the concentration you dissolve, these amalgams may be still liquid in the mercury that is still liquid, or these amalgams can solidify and form, and if you stir them up, you can form little beads of reactive compound. The reason you use the mercury is it acts like a solvent, diluting the reducing agent, which is the zinc. This can slow down reactivity and prevent side reactions. It can also allow the reaction to be more controlled, so if it's exothermic, it doesn't get out of control. Now, the exact mechanism is not well explored, and as a result, we're not going to look at the mechanism. Suffice to say, zinc transfers electrons, and the H plus on the HCl becomes H minus, and presumably in this reaction we are actually removing water, removing the oxygen as water. But we're going to just leave it at this. However, we can have a problem with the Clemmensen reduction. You see, sometimes you want to make a hydrocarbon and you want to remove a functional group without affecting other functional groups. For example, suppose I wanted to take this molecule and I wanted to make a hydrocarbon, or I wanted to reduce this molecule so as to get rid of the OH group, but I wanted to retain the aldehyde. So I wanted to make this. There we are. Okay, I want to get rid of the OH. Well, immediately what comes to mind is, all right, I know how to get rid of a C double bond O, so why not oxidize this to a C double bond O, this OH, because we've learned the Clemmensen reduction. But I have a problem. Many of my oxidizing agents, powerful enough to oxidize an alcohol, will oxidize the more easily oxidized aldehyde. That is, aldehydes go to carboxylic acids much more easily than alcohol to ketones. So if I use CrO3, for example, I'm going to oxidize the aldehyde. Well, we learned a few Scribblecast lectures earlier that we can react this molecule, an aldehyde, with ethylene glycol. And if we hit this with anhydrous HCl, we can drive this reaction through to the full acetal. If we do this, we get a molecule that looks like this. Now the full acetal is stable in base, and as long as we're in base, it will not be affected by oxidizing agents. Now normally you use CrO3 in acid, but we can use CrO3 in neutral conditions, and if we're careful, we can retain our full acetal. If we use neutral conditions, we can actually oxidize this alcohol to the carbonyl. Fantastic. That means we're ready to reduce the C double bond O. Without affecting the aldehyde functional group, which is trapped in or protected in the full acetal. But we have a problem. The Clemmensen reduction, zinc, mercury, HCl takes place in acid. Our protecting group is not stable in acid. That means it's going to go back to the aldehyde. And when it does, the zinc mercury will reduce it. As a result, we have a major problem here in that our reagent is not compatible with the protecting group. Ideally, we want some kind of reagent that will allow us to do this reaction, and do it under basic conditions. Conditions that will retain the protecting group, thereby reducing only the carbonyl. So you can see the desire to have an alternative reagent. Well, what we're going to do now is look at the reagent, and then we'll come back to this and finish off this reaction. The reaction that uses a reagent in base is referred to as the Wolff-Kishner reduction. the Wolff-Kishner Reduction. Okay. Now the Wolff-Kishner reduction also reduces to hydrocarbon, but it goes through a different procedure. It involves two steps. The first step is reaction with hydrazine. Now, do you remember what hydrazine will form? Hydrazine will form a hydrazone. The second step is reaction and base. Now, you can use hydroxide and water, ethoxide and ethanol, or any base really will do. Potassium, I'm going to put in tert-butoxide, OC bracket CH3. Now, if you use tert-butoxide as your base, what is your solvent? Well, your solvent obviously has to be tert-butyl alcohol. Why? Note that you always choose as solvent, if possible, the conjugate acid of the base you're using. The reason is if you use tert-butoxide in water, the tert-butoxide will deprotonate the H2O, giving you hydroxide. And so your base will not be tert-butoxide, it would be hydroxide. So if you want to use tert-butoxide, you pick the conjugate acid, because if the tert-butoxide deprotonates tert-butyl alcohol, you get back tert-butoxide. You always have tert-butoxide present. So we always choose a solvent, the conjugate acid of the base we're using. Now in this case it doesn't matter because it's just acting as base. And if you complete this process, the Wolff-Kishner reduction, as expected, will reduce you to the hydrocarbon. Now, of course, it would be nice if we understood what's going on in this reaction. So what we're going to do is we're going to look at the reaction mechanism for both steps. The first step, the reaction mechanism, is quite simple, the hydrazone formation. You see, if I take R, I'm going to use R and R prime here around my C double bond O. I just follow the normal mechanism that we observed for imine formation. That is, formation of hydrazone follows the exact same formation of imines, although the pH can vary differently. It can be a little more acidic because the lone pair is less basic in this case. But if we hit this molecule with hydrazine, we will get R, C, O minus, R prime, and then we have our NH2 group, which acted as a nucleophile. It's positively charged now. We have it attached to an NH2. Well, now we can do a series of protonation, deprotonation steps. So minus H plus, for example, gives me RC. We still have the O minus. And now a lone pair here. Go down, plus H plus, give me R, C, O, H, R prime, nice. Okay. We can now protonate one more time, plus H plus. Gives me the good leaving group, water. H2O plus is attached. I still have my NH, NH2. Lone pair here, R prime. Minus H2O. And that gives me, of course, a carbocation here. RC plus. If H2O leaves, R prime. And H. Of course, that's resonance stabilized. Dump in some electrons here. So I can draw a resonance structure. Get RC double bond N. We have R prime. We still have an H on the nitrogen, which makes, I guess this would be a hydrazonium ion. And now we go minus H plus. And we have our hydrazone, which, if it was based on acetophenone, the starting reagent, this is a acetophenone, then we would have made acetophenone hydrazone. And there's a lone pair there. Now this first step is not new. Okay? It looks like a B. That should be a minus. This first step, I'm going to rub out the tert-butyl alcohol here. This first step is not new. You've seen this step in imine formation. It's the exact mechanism that we had in imine formation. We've also covered the chemistry of hydrazones, phenylhydrazones, 2,4-dinitrophenylhydrazones, semicarbozones, and oximes. So the first step is review, if you like. But what happens next, once we form the hydrazone, is really the key to understanding how we get to the hydrocarbon. Let's take a look at that. Okay? So let's examine the second step. So I'm going to now go through, and I'm going to up here draw because I don't want to rub off the initial reaction. I'm going to draw my hydrazone. Need a bigger eraser. Huh? And what do we have? We're going to have some kind of base reacting with the hydrazone. In our case, we've used two tert-butoxides. So I'm going to draw R, C, R prime, double bond N, and H2. Put in the lone pairs. There we are. That's a hydrazone. And we're going to react. I'm going to just put RO- as my base. In fact, the base will come in and grab a proton. So I'm going to have RO- come in, and it's going to leave as ROH, which in this case was tert-butyl alcohol. But it doesn't have to be. And I will have made RC double bond N. I will deprotonate the nitrogen. If I do that, I get NH minus here. And we have an R prime. Now, if I deprotonate this, I can draw a resonance contributor. for this, R, C, R prime. Okay, where I move these two electrons to create a double bond between the nitrogens and move the pi electrons out on the carbon. And so what that does is create a lone pair on the carbon that's negatively charged. And now I have N double bond NH. Well, obviously, as you can imagine, C minus is very basic and would pick up a proton. Where would it grab the proton? It would grab it from the alcohol in solution. So I would have alcohol, ROH, come in and leave as RO minus. And that would put an H on that carbon. So it's now a CH R prime. And then I've got my N double bond NH. Well, the whole process can happen one more time. That is, base can come in and deprotonate the nitrogen on the end. So if I have base come in and deprotonate the nitrogen, so we'll have RO minus come in, produce ROH, and we get the proton being pulled off, RCH, R prime. We have N double bond N, get another lone pair, that ends now negative. We're set up to kick out a C minus group. Now wait a second, C minus? C minus is a terrible leaving group. It's a super powerful base. Why would you get a C minus? It's because of the awesome nature of the formation of the product. You get the huge release of energy. Dinitrogen, if we dump this lone pair into a pi system, we get a triple bond. Breaking this bond, we release N2 gas. N2 gas release is irreversible. Get minus N2 gas. Huge release, very stable, and we get the consequence of that, of course, is you get this carbanion. Carbanions are extremely basic. This is not going to hang around very long. What's going to happen is you're going to get, let's go here, yes, take it right down to here where we've got some room. You're going to have ROH come in, and that C minus is just going to rip a proton off of it, giving you alkoxide minus or hydroxide, whatever your base is. And then notice what you've done. RCH2 R prime. Wow. Now, one of the things I did in here was intentional. You get used to writing equilibrium arrows in these mechanisms, and you really have to think about it. You notice I left it out here. N2 gas will not add back to a carbocation. It's too carbanion. It's too stable, and so I drew a straight line, meaning that step is irreversible. Let's think about the other steps. Okay. Well, in actual fact, this negative N is resonance stabilized, and the proton could go back. So indeed, you could have going back ROH in this step, going back to RO minus. This reaction, though, is often written with straight arrows as irreversible. The next step as well, picking up a proton on the carbanion. This is essentially irreversible. It is highly unlikely you would deprotonate a carbon as opposed to deprotonate a nitrogen. So it's more appropriate to have an arrow here. Right? And deprotonation in the second step, okay, occurring here is also typically drawn as irreversible, although you could envisage it as an equilibrium. I'm going to be very lenient on you in this case, and so in your notes I've just drawn this reaction with straight arrows, and that is fine. So don't worry about the equilibrium here, but note the last step is totally irreversible. The loss of N2 gas. Once that happens, the reaction goes to completion. Now what's nice is notice this reaction took place in base. And so we can come back now to the last step of the reaction we were looking at with regards to reduction of this molecule to a hydrocarbon while protecting the aldehyde group. So we had two CH2s here. So as you recall, we took this aldehyde and we reacted it with ethylene glycol, and we put on the protecting group. A protecting group that's only stable in base. What this means is when you do reactions where you have such a protecting group, you have to keep in mind the stability of the protecting group as to what reagents you use. So you had the full acetal formed here. You have the full acetal, lo and behold, this group protects you from oxidation, reduction reactions as long as you're in base. Now, this is where you have to give thought to that because, you know, we don't know how to get rid of an OH and put an H on, but I remember that, hey, I can get rid of C double bond O, so I can oxidize this. Well, normally, you use CrO3 and acid, a powerful oxidizing agent, but the acid would destroy your full acetal. So that's the bit about neutral conditions. That's why we put neutral in. CrO3 under neutral conditions to prevent the acid from destroying a protecting group. Whenever you use a protecting group, you have to keep that in mind. Well, that converts, of course, the CH3, the OH, to a double bond O. Now we have CH2, CH2, and we're back to where we were. Excellent. With a full acetal. Now we have the ability to get rid of that double bond O. We do the Wolff-Kishner. 1 H2N, NH2. And I said you could use any base, so this time let's throw in some hydroxide. What solvent would I use with hydroxide? The conjugate acid, which is water, and sometimes you actually have to heat this reaction. So a triangle is fine as well. Putting the triangle in or leaving it out is fine at this point. And that would get rid of the double bond O, giving me a CH2. Still have my original CH2s. And now, because we're in base, I still have the the full acetal. Now, take this full acetal, hit it with acid, and notice you've made the molecule with the aldehyde group, and you've been able to do this reduction without harming your aldehyde. Of course, you also get back the ethylene glycol. So there you have it. It is advantageous to have reagents that function both in acid and in base, so that if a reaction is acid sensitive, you can use the base. If it's base sensitive, you can use the acid conditions. The last reduction, which was important, that we need to look at, is the reduction to amines. Carbonyl groups in aldehydes and ketones, as we've said, could be reduced to alcohols. We examined that last scribblecast. Reduced to hydrocarbons. We've just finished looking at that with the Clemmensen and Wolff-Kishner reduction. And can be reduced to amines. How can you do the reduction to amines? Well, the reduction to amines is facilitated by a reaction we've already learned, and that is imine formation. That's correct, imine formation. Imines, remember, are those molecules where you've reacted a carbonyl with an amine, okay, and you've done so at a narrow pH window, usually pH 4 to 5, something like that. So you take an aldehyde, for example, and you react it with H2N, CH3, and pH 4 to 5, and you get imine. Now, just like C double bond O, C double bond N can be reduced catalytically. You can hit it with nickel and H2 gas. You may or may not need heat. So we often put a triangle, which just could mean room temperature. Triangle in this course, remember, means enough heat to drive the reaction. And H2 will add across the double bond. There's nothing special about this double bond compared to a C double bond O. It's a little less polar, that's all. And so we can add an H across the double bond. If we do that, what did we get? We've gotten an amine. So what you see, we've gotten a new amine, is that we can reduce to amines through a two-step process. One, reaction with some kind of amine. Okay? Now, this would even work with secondary amines. Remember, secondary amines produced enamines. I'm going to make this a primary. And then two, metal hydrogen, like nickel H2 gas. Platinum H2 gas. Okay. Now, if you had used a secondary amine here in this reaction instead, if, for example, I had replaced this, let's do it down here. If I had taken CH3, CH2, C double bond OH, and I had hit that with HNCH3 twice. Remember, secondary amines can't lose a proton, so they can't form an imine. The resultant iminium ion would be unstable, and so you deprotonate at the carbons, right? And you produce, if you remember correctly, you produce an enamine. An enamine. And so if we draw the enamine that would form here, form an enamine, such that if you did the reduction now, nickel hydrogen gas, you would hydrogenate the carbon-carbon double bond. And so whether or not you use a secondary and go through an enamine, or you use a primary and go through an imine, the hydrogenation is still possible, and you will get an amine. Primary amines through this process end up giving you secondary amines, and if we use the secondary amine and we carry out this reaction, we get a tertiary amine. There you go. So this bottom went via an enamine. And this top reaction went via an imine. So again, you'd write 1 amine, 2 nickel H2. Okay, so reduction to amines involves either imine or enamine intermediates. Okay. Now, why do this reaction? Why not just do a simple substitution? After all, can't I take CH3, CH2, CH2Br, hit it with, let's use the primary amine, H2N, CH3, methylamine. This is a powerful base, powerful nucleophile. You've got a primary. You're set up really nice to do an SN2 backside attack. Couldn't this guy just simply do a backside attack, forming the protonated amine, which would then deprotonate, and I'd get this amine? Why go to all the trouble of using the aldehyde? Why go to all the trouble of using the aldehyde? Hitting it with, in a two-step process, with nickel hydrogen. Wouldn't the one-step process be simpler? That should be a 2. Well, the answer is it looks simpler, but in actual fact it's not. First off, it's always useful to have two different reaction paths. I mean, you might have aldehyde, you might not have bromide, but there's a trick. Remember here, in this case, that the nucleophile in the SN2 can also act as a base, allowing E to occur and producing alkene. And the problem here is this nucleophile is also a very powerful base. And because it's such a powerful base, your impurity concentration of alkene increases and yields are reduced. Okay? Furthermore, the product that you form can subsequently start attacking some of the propyl bromide. This attack may be limited by steric hindrance effects, but you may get some further impurities of a tertiary amine. So your yield of the desired amine may be low yield. Whereas in this reaction, you get very good yields, high yields. It's very important when you compare reactions, you don't just compare the desired product, just don't focus on the one mechanism. You consider all mechanistic pathways and try to predict or get an idea of product yield. The reduction to amines from aldehydes gives you a good yield of the product N-methylpropanamine. Okay, well that's it for reduction. We've finished off looking at reduction of aldehydes and ketones to yield alcohols, which was covered in the last scribblecast, to produce hydrocarbons, alkane-like molecules, which we did earlier in this scribblecast, and just finished off production of amines, reduction to amines, which goes via the imine or enamine derivatives, followed by catalytic hydrogenation. Next scribblecast lecture, we're going to examine the oxidation of aldehydes and ketones. So, I'm Dr. Brian Lloyd. This is my scribblecast. Thank you very much.